Hello everyone, welcome to this presentation on the Edmond Karp algorithm. My name is Tom and with me is Aaron, and today we'll go through it and basically give you an understanding of what the algorithm does and how it actually works. So the aim of the algorithm is, as you can see here, to find the maximum feasible flow through a single source, single sink flow network. Before we go into explaining what the algorithm does, there's a few important definitions you need to know. So a graph is basically a set of vertices, or you can think of them as points, connected by edges, or you can think of those as lines. Edges are defined by the two vertices it connects. However, in a directed graph, all the edges have a set direction. So the edge that connects U to V, for example, is denoted by UV. So if we were to look at this example, this is an example of a directed graph, because as we can see, there's vertices connected by edges. However, the edges have a set direction, so you can go from A to B, but you cannot go from B to A. So what a flow network is simply a directed graph in which each edge has a capacity, denoted by CU of V. So basically what the capacity is just the maximum amount of flow that can pass through the edge. Obviously it's not negative. So you can represent a flow network by this notation here, where capital V is the set of vertices in the graph and capital E is the set of edges, UV. The source and the sink of the network are essentially start and finish vertices, or you can call them nodes, it means the same thing, of the network, and they're represented commonly by S and T. The flow along an edge is the amount of the capacity being used on the given edge, denoted by F of U of V. There's certain properties that the flow must satisfy, and that is that the flow through a certain edge can never exceed the capacity, which sort of makes sense. You can't send 6 things through an edge that can only hold 5. And then the flow going into a vertex must equal the flow going out. So as you can see, we have a sort of mini example here, and we can see that the flow is on the left and then the capacity is on the right, and we see that the left value never exceeds the right value in any of these edges. And we can also see, for example, if we take O, for example, you have 3 flow going in and then 3 flow coming out, or 3 plus 0 flow, which is 3. Okay, so the residual capacity of an edge, UV, is basically defined as the capacity of the edge minus the flow of the edge if that edge belongs to the set of edges in the flow network. It's, however, defined as the flow between the edge VU if VU is an edge in the flow network and 0 otherwise. So now we can look at E of F, and it's essentially defined as all the edges in the set of edges of the graph where the residual capacity is greater than 0, and the residual network of a graph is essentially defined by the set of vertices as well as this E of F here. So an augmenting path is basically a path from the source to the sink in the residual graph. So if we look at our mini example here, S to O to Q to T would be considered an augmenting path, and the corresponding residual capacity of an augmenting path is simply just the minimum of the residual capacities of the graph, of the path, sorry. Okay, so now we're going to look at the basics of the algorithm and basically explain how it works. So we begin by initializing the flow F in the graph to 0, and we let our initial graph that we're given basically be our first residual graph with flow 0, and then we perform this while loop. So while there's an augmenting path in the residual network, we first use breadth first search to find the shortest path from S to T, and this will be our augmenting path P. Then we augment F using P, and then we update our residual graph. And then once this is ended, this ends once there is no, obviously, more augmenting paths from S to T. And then your maximum flow is the sum of all the flows leaving the source node once you've reached your final residual network with no more augmenting paths. And something to take note of is that the shortest path is with respect to the number of edges, or the number of essentially jumps from your source to your sink, not to do with the flow or the capacity of the edges.
Right, this is a simple example of a flow network in which we'll run Edmond Karp on to show you the basic idea. Here we have selected an augment path using breadth first search, which we will now then augment F using P, which is basically finding the maximum flow along this path, also known as the capacity or residual capacity, and push this along the given edges in the augment path. This results in a critical edge being created in the new residual network shown here. This is our residual network after having updated the graph through this step here. This became our critical edge, or was our critical edge in our augment path, and it resulted in a strict back arrow here. To explain this forward and back arrow, it's a result of the total capacity of this edge originally was 7. Having pushed 3 forward, it results in us still being able to push 4 forward and being able to push 3 back. And now that we've finished with this residual network, we return to the start of the loop, begin using breadth first search again, and find a new augment path. This is our new augment path shown in orange. I would just like to quickly point out this edge has now become, or reached its full capacity, 6 out of 6, and so is now the critical edge of this augment path. We were only allowed to push 3 along these edges due to this graph having shown previously, having been adjusted beforehand, has been reduced down to only allowed a further 3 to be pushed forward. After having augmented F using P and updating our residual network, we find this to be our critical edge. At this point, it's just a matter of running through the loop and finding new augment paths and finding critical edges and adjusting your network. Another path of length 3 is shown here, with the critical edge turning out to be this one at the end. Having previously been used, we were only allowed to push 4 along this path. After augmenting F using P, we continue and find this residual network. This is our new augment path of length 4 after having run breadth first search. We find this edge of length, or of capacity 5, to be our critical edge, and results in us pushing 5 along the edges in orange. Applying this gets us another residual network, which we run breadth first search on to find our final path. This is an example of where we end up pushing back across an edge which is once previously a critical edge in one of our augment paths. This was allowed due to the fact we are allowed to push back across edges. Our critical edge in this final augment path was this one at the top. Running breadth first search on our final residual network results in no further paths being found from source to sink. Therefore, we're finished. Our maximal flow for this network in the end turns out to be 11 plus 6, all of the flow coming out of the source, which is 17.
Okay, so now we will look at the complexity of the algorithm. So one thing we need to know for complexity is the number of iterations the algorithm takes. Now we know the number of iterations for this specific algorithm is equal to the number of augmenting paths. So let's begin by denoting our graph as before as G v of E, and source and sink as S and T respectively. Then for all the vertices that belong to V that aren't the source or the sink, then the shortest path we denote by this. In the residual network G of F, strictly increases with each flow augmentation. So each augmentation has at least one critical edge that sort of vanishes from the residual network, as we saw before. If an edge, UV, vanishes, then we know it cannot appear until the flow from U to V has decreased. Now we can show that from the time UV becomes critical to when it next becomes critical, that the distance from the source to U increases by at least 2. So using the information in the previous sheet as we showed, we have that the shortest path in the residual network is equal to from S to U is equal to the shortest path from S to V plus 1, which is greater than or equal to the shortest path in the residual network from S to V plus 1, which that equals the shortest path in the residual network from S to U plus 2. So the maximum distance from U from the source, if it ever becomes unreachable from the source, is the number of vertices minus 2. After the first time, it becomes critical at most the number of vertices minus 2 over 2 times. We know that there are E edges, so the total number of possible paths, which equals the number of iterations, is of big O EV. Now we know each iteration runs in big O of E time, as it must go through at most all the edges in the graph. Hence the time complexity of the whole algorithm is big O of E squared times V.